So we will open the next session. Next paper will be entitled Multiplexed Nanomaterial-Based Sensor Array for Detection of Pathogenic Medicines. It will be delivered by Dr. Mandal and associating Mr. Chu or Dr. Chu. Okay?
Yeah.
So please, the floor is yours.
Yeah, thank you. So, thank you.
Please.
Thank you, sir. Thank you, everybody. So, my topic is multiplex nanomaterial-based sensor array for detection of pathogenic microbes. So, for me, that I will give some introduction why this is important and why it is really needed. So, it is really happening with us every day, every time, every families. So, here is I put some slide about the some common diseases, that is common cold, flu, chickenpox, measles, and hepatitis A, B, C, D, E, meningitis, and many others. So these all are viral infected diseases. So what is the happening here? And why I am giving this example? Because the common cold and flu, it is always happening in family with the babies. A doctor always misinterpreted this is common cold or flu. And what they are doing, they are just thinking something, their mind, and they give some medicine for 2 days medication. If the symptoms is changed, they will change the medicines. So that is very, very unjustified for babies. Why? I have baby. So it is very problematic for now for me also. So what happening there? When doctor gives some medicine for 3 days, 4 days, 5 days, and if symptoms it changes, they will give another medicine. So it is important. First important is detection and clearing the confusion. What is this? Is the common cold or this is the flu from other any things? And another same thing, when the chicken pox and measles is happening with this baby, what happening there you can see, I give the photos here. So you can see the symptoms is near about same, the outlook, appearance is same, and symptoms also near about same. There also the confusion. And in case of hepatitis A, B, C, there are also same things happening. And I put there 2 type of meningitis. Meningitis, you know, that they are brain membrane meningitis. Meningitis, there is something happening that is meningitis. So that is happening with 2 type of pathogens. One is virus, means virus affected. One is bacterial affected. But both symptoms is near about same. If you give the meningitis medicine, particularly what you are thinking, it is meningitis, you have to, doctor thinking I have to give some medicine for meningitis. But they have to detect first, this is viral, means viral, not viral, virus affected or bacterial affected. So, what nowadays the traditional procedure is central fluid. Our central fluids, they are checking central fluids and they are checking for white cells, protein and glucose level. If the white cells, protein and glucose level is higher, they have some threshold. If the higher than that threshold, they are thinking this is bacterial infected. If that is lower, they are thinking it is viral. So here is also one confusion. If the this virus affected is very early time or very minute quantities, that time it will also, yeah, it's bacteria, it is happening with bacteria, that time also it will give the low concentration of white cells, protein and glucose, so doctor will confuse and you will be mistaken. So So this is another many common diseases: yellow fever, nowadays monkeypox, and AIDS, UTI, malaria, also HPV, human papilloma virus, that is responsible for many cancers. So we have to detect first, particular which causative is there, which pathogen is there. Then doctor can give the proper medicine and it will be better. So why it is important, again I will show you that traditional detection method, that is you can see here immunological assay, PCR, RT-PCR, and cell culture, you know, the PET, PET, yeah, SPECT scanning, MRI, and also ultrasonography. That is time consuming and cost consuming, very high cost. So we need for doctor, for patient needs very early stage and very immediate. It should be confirmed it is this type of disease and causative by some this pathogen. So that's why it is very important to detect first. So how you will detect first? I will tell you later. Now I am given some data here. You can see there's some medical error and economic burden for this misconception and detection. You can see the one US agency, they calculated that infectious disease, the economic burden is near about $120 billion. And for, you can see here is the this slide, it is the very small letter, but for the this medical error near about $46 billion is normally people given always for medical error. They can't understand the disease, which type of disease and what is happening there, and other many medical error. So this economic burden we should minimize. So our main goal is this: stop the medical error and save the economy as well as the life. How it is possible? So our scientists, not only now, very beginnings and now also, they're developing identifying many markers, gene markers and other protein markers for every particular diseases. They already developed. They already know. So here is some presentation in here. In case of yellow fever, I presenting here. In case of HIV and influenza A, here is the marker gene is OS here, OSSL, this marker gene. In case of Streptococcus pneumoniae, there is the CPSA gene, and in case of mumps virus, there is the NH or SH gene. This is the marker gene. So if we identify that marker gene, particularly marker gene immediate, then we can identify this is the causative for pneumonia or causative for mumps virus. This both virus the symptoms is near about same. So what we are doing here? So nowadays this is the COVID-19 era. So we give some example as a COVID-19 detection. So what? Here, this is the COVID-19 in SARS-CoV-2 genome sequence. Here, particularly that marker gene is nucleocapsid protein N. So if we detect many type of that corona virus is there, we know the SARS-1, SARS-2, MERS, they all are corona groups. But in case of corona 2, means SARS-CoV-2, there is particularly this position, the nucleocapsid protein N region, some marker gene is there. If we detect from our sample this particular gene, then we can detect this is the SARS-CoV-2. So we give some example detecting with this our material with this COVID-19. So here we give some sequence. So one sequence we are making just replicate of this nucleocapsid protein. So what we are doing, we are synthesizing one 3D covalent organic framework structure. That covalent organic framework structure look like a little bit graphene oxide. So it is the characterization of this structure. This is really covalent organic framework or not. There's many characterization we are doing here, and you can see here. This is the porosity. It is a highly porous material. We give here the bead is measurement, and this is the pore size is 22 Armstrong, and there is the under ACM and TM, it is look like sheet. You can see this is the ACM image, sheet-like structure, and here is the lower part. It is the TM structure. See, and how it is synthesizing in the process. 24 hours we are it is taking to synthesize. So how it is happening? First it is fiber, synthesize some fiber assembling and making this sheet-like structure. So what we are doing here? What is the mechanism and what is the you can see. So we synthesize, artificially synthesize some probe. That probe is just replica of the particular DNA sequence of the particular disease. Just replica of that. So that probe is attached to it some some tag, process tag. So when this tag is we are using with a particular DNA sequence, that time we are mixing with our CF nanoseed, covalent organic framework nanoseed. When we putting in with the sample, that time that covalent organic frame nanoseed is attached with this covalent bonding with this seeds, and this process is off. And after attaching after given the sample, that is the which is the replica sample, that if we put with that sample, what happening there? Then the replica DNA and other side, which DNA is two strands. So when two strands is coming each other near about, and hydrogen bonding is happen, and that hydrogen bonding is more than higher force than covalent bonding, and it is detaching from the seeds, and then fluorescence again coming. So if the one disease is different level, means early stage level, there the presence of that particular virus is less, so it will be detached less. If it is higher concentration, and then it will be detached higher levels, the fluorescence intensity will be different. So we can quantitative and qualitative detection from this test. So here we give some example. You can see the P1 is our particular probe what we are taking with the fluorescence material. When we are putting our COF with that material, fluorescence is go down. No, means there is quenching, 100% quenching in case of hair. It's not possible 100%, near 99% is quenching. When we putting the sample, any type of fluidic sample in from throat, nasals, from blood and others, we are adding there. If there is a particular that gene sequence is present, it will be again it is fluorescence is increasing. So this graph is increasing. It is first it was here. When we putting our CF material, it is decreasing. It's increasing. So from here you can detect. And that graph only you are showing here is. So for different concentration of the particular gene sequence we are taking and we are measuring there, and there is particular graph is there, and it is increasing. The process is increasing. So that's the way we are detecting our COVID-19. How? At first we taking the nasal swab and throat swab both. You can see when the fluorescence for the P1 means probe, our probe is this much higher, and the T1 is it should be here, and nasal swab and throat swab is again increasing. That is, and here we are taking something DNA sequence for the random DNA sequence means there is no similarities with the particular gene sequence, and other sequences only single mismatch DNA means there is all particular DNA sequence will be there, but one amino acid will be different. So you can see here when the only probe is here, the red one is crossing here. After decreasing, when we putting our material, it is decreased, but when target is there, that is only increasing, process increasing again. And other only single mismatch DNA, it is very little, and when the random means anything is coming, it's not given the any process. Means our material selectivity is very high. Only particular disease we can detect through this detection method. So you can see here the direct evidence under ACM microscope. We taking these images where how the DNA is attaching with the cells there, and many other methods, normally conventional method. That method given this type of many detection, but our this process is that sensitivity is 2 picomole. We can detect if even 2 picomole of disease virus material is there, we can detect from there, and within 5 minutes only. So using this is the 2.301 picomole. So using these methods, we developed one small device. The device is very small, like a matchbox. So here you can using the your any type of